Nanophotolithography is a cutting-edge technique used to fabricate plasmonic waveguides with high precision. It involves using light to pattern nanoscale features on a substrate, crucial for developing advanced optical devices. This process enables the creation of intricate structures that guide light at the nanoscale, essential for applications in telecommunications and sensing technologies. Nanophotolithography enables precise patterning at the nanoscale, crucial for developing advanced plasmonic waveguides. This technique involves using light to transfer geometric patterns onto a substrate, allowing for the creation of intricate structures. It is essential for applications requiring high precision and miniaturization in photonic devices. Photolithography offers a resolution greater than 100 nanometers with high speed and repeatability, utilizing a lift-off process. Electron beam lithography achieves around 20 nanometer resolution, but is slower and less repeatable. Nano-imprint lithography is industrially used. The process involves laser light, photomask substrate, aqueous development, chromium etch, and photoresist strip. Photolithography, limited by the diffraction of light, operates above 100 nanometers. Plasmonics, however, enables sub-wavelength operation, achieving resolutions around 50 nanometers. By utilizing near-field coupling between closely spaced metal nanoparticles or planar plasmonic waveguides, information can propagate below the diffraction limit, offering a significant advancement in nanofabrication techniques. Plasmonics harness surface plasmon polaritons, SPPs, for sub-wavelength information propagation. Plasmonic waveguides enable this by confining light below the diffraction limit, as detailed by J. Dion et al. And Meyer et al. This technology offers a significant advantage over traditional photolithography, allowing for much smaller feature sizes and enhanced precision in nanofabrication. Plasmon printing offers a significant advantage over traditional photolithography by achieving a smallest feature size of approximately 0.11 Li compared to photolithography's LL. This is achieved through the use of a photoresist, substrate, and mask with exposure and development processes as detailed by P. Kick et al. In 2002. Field enhancement in plasma nanospheres significantly amplifies electromagnetic fields at the nanoscale. This phenomenon is crucial for applications in sensing and photonic devices, as it allows for precise manipulation of light beyond the diffraction limit. Understanding the field profile of these nanospheres is essential for optimizing their performance in various technological applications. Plasmon printing leverages localized surface plasmon resonances to achieve high-resolution patterning. This technique utilizes the interaction between light and metallic nanostructures to enhance optical fields, enabling precise control over nanoscale features. The work by P. Kick et al. Explores the potential of this method in material science, highlighting its applications in creating intricate designs with exceptional detail. Final resolution in plasmonic printing is determined by the interaction of light with metallic nanostructures. This interaction allows for sub-wavelength patterning, surpassing traditional optical limits. The precision achieved is crucial for applications in nanotechnology, enabling advancements in fields like data storage and photonic devices. Plasmonic waves exhibit a larger K-vector than light waves, crucial for surface plasmon resonance. Key sources include helium-neon lasers at 632.8 nanometers, excimer lasers at 248 nanometers, and laser diodes at 1550 nanometers. The relationship between dielectric and metal layers is defined by the equation surface plasmon K gain E dielectric plus E metal Ge 0. Excitation of surface plasmons can be achieved using a high-index medium, such as a prism at the air-metal interface. Additionally, periodic structures leverage the Bloch theorem, where the k-vector is periodic with a reciprocal lattice vector, enabling excitation through grating. These methods enhance plasmonic wave interactions effectively. Excitation can be achieved using dots, where quantum dots interact with surface plasmons to enhance coupling. An array of dots further amplifies this effect by creating a collective resonance, improving the efficiency of plasmon excitation. These methods offer innovative ways to manipulate light at the nanoscale, crucial for advancing photonic technologies. Methods of excitation include prism coupling, grating or roughness coupling, and end-fire excitation. Prism coupling, known as the Kretschmann technique, is used for metal insulator and insulator-metal insulator setups. Grating coupling applies to metal insulator, insulator-metal insulator, and metal insulator-metal configurations, while end-fire excitation is suitable for metal insulator-metal and insulator-metal insulator setups. Each method utilizes incident light and evanescent waves. Prism coupling efficiently excites MI, IMI setups and asymmetric modes with excitation angles dependent on film thickness. Despite high efficiency and mode selection flexibility, it requires precise gap and beam adjustments, leading to stability issues. The system is costly due to the high index prism and adjustment mechanisms, yet offers experimental adaptability with a detachable prism. The inherent roughness of the metal film creates a distribution of inelastic scatter centers for surface plasmon polaritons, leading to scattered light. This method faces challenges like low intensity and inhomogeneous distribution. A sharp microscope tip scatters part of the local optical near field into the fiber, directing it to the photodetector. End-fire coupling involves direct excitation from the waveguide's end, utilizing butt coupling of polarization-maintained fiber at the input and a single-mode fiber at the output. Key components include optical index match gel, a lens system, infrared camera, thermoelectric cooler, tunable laser or electroemissive light-emitting diode at 1.55 micrometers, and an optical spectrum analyzer. Grating coupling offers high efficiency and can excite any guided mode, making it ideal for compact, stable, and cost-effective waveguide integration. However, it requires complex calculations and advanced fabrication with fixed device parameters post-fabrication. Alternative methods include tapered, prism grating, and holographic coupling, each with unique advantages and challenges. Grating structures are pivotal in coupling light into waveguides. Their shape and periodicity determine the efficiency of light coupling. By adjusting the grating's parameters, specific guided modes can be excited, enhancing device performance. However, post-fabrication adjustments are limited, necessitating precise initial design and fabrication techniques. Corrugated surfaces, whether perforated or imperforated, can convert plasmons to light and vice versa, even with mercury lamp light in photolithography. Periodic structures such as gratings exhibit varying k-vector values, facilitating light-plasmon coupling. The surface plasmon wavelength is directly proportional to the lattice periodicity, enhancing the interaction efficiency. Luo et al. Demonstrated interference patterns achieving a resolution of 50 nanometers, as reported in Applied Physics Letters and Optics Express in 2004. These studies highlight the potential of interference techniques in enhancing resolution, crucial for applications requiring precise patterning at the nanoscale. Superlenses leverage negative refractive index materials, defying Snell's law to achieve subwavelength resolution. These left-handed materials, LH, enable imaging beyond conventional limits. With refractive indices of N-1, they contrast with right-handed materials, RH, where N-1 allowing unprecedented source-to-image fidelity. This technology revolutionizes optical imaging, offering new possibilities in fields requiring high precision. Transmission through unperforated and perforated surfaces is crucial in optics. Bonnard et al. Demonstrated this in 2003 with a 0.08 micrometer thick surface. Jiao et al. Further explored these concepts in 2005, highlighting the impact on electromagnetic wave behavior. Understanding these principles aids in manipulating light for advanced optical applications. Interference patterns arise when incident light at LFU 436 nanometers and energy E22843 millielectron volts interacts with the medium. Luo et al. Demonstrated how these patterns can be manipulated to enhance optical properties, crucial for applications in photonics. Understanding these interactions is key to advancing technologies in optical communications and sensor development. The periodic corrugated setup, as detailed by Luo et al. PTT, offers a resolution of 25 nanometers with a G-line of 436 nanometers. This configuration enhances light manipulation, crucial for advanced optical applications. Understanding these setups is essential for developing efficient plasmonic structures, which we'll explore next. Plasmonic structures are categorized into planar and non-planar types. Planar structures include simple metal insulator, insulator metal insulator, and metal insulator metal waveguides, as well as Bragg gratings. Non-planar structures encompass nanoparticles and nanoshells, offering diverse applications in photonics and sensing. These configurations enable precise control over light-matter interactions. Material choice is crucial in plasmonic structures. Metals like gold and silver offer negative permittivity and low loss at specific frequencies, such as 1.55 micrometers for gold and helium-neon laser range for silver. Insulators with positive permittivity ensure substrate compatibility or function as photoresists, including silicon dioxide, benzocyclobutene, and polymethyl methacrylate for various lithography techniques. Choosing the right substrate is crucial. Silicon substrates, including silicon on insulator and oxidized types, are common. Silica substrates like quartz and fused silica glass offer alternatives. Indium tin oxide-coated glass is used for electron beam lithography due to its low conductance. Each substrate type has unique properties that influence the fabrication process and final device performance. Fabrication involves photoresist spinning using PMMA for E-beam lithography and BCB for photolithography. Exposure utilizes electron beams via scanning electron microscope, X-ray, ultraviolet, or visible light. Development employs an aqueous developer. Metal deposition is achieved through E-beam evaporation, followed by a lift-off process. This sequence ensures precise patterning on substrates. Sputtering 20mm SiO2 on a silicon wafer is followed by E-beam evaporation of a molybdenum or titanium adhesive layer under vacuum conditions. Gold is then E-beam evaporated at 24.4 nm thickness. The lift-off process involves both steel and ultrasonic baths. SiO2 is sputtered on gold, with an option to replace SiO2 with 15mm BCB applicable on SiO2 substrates. Cyclotene is applied on a silicon wafer using an adhesion promoter, followed by spin coating at 1000 revolutions per minute for 10 seconds and 2000 revolutions per minute for 30 seconds. Soft and hard bakes are performed at 210 degrees Celsius and 250 degrees Celsius, respectively. Photoresist S1813 is spin-coated, pre-baked, exposed, and developed to achieve undercut, enhancing lift-off quality. Gold is deposited via electron beam evaporation, followed by acetone and isopropanol rinsing. In MEM fabrication, substrates like oxidized silicon or silicon dioxide are used with insulators such as cyclotene or silicon dioxide. An adhesion promoter may be applied if necessary. Ultraviolet light and a mask are used with photoresist to create an undercut, enhancing lift-off quality. Gold is deposited on the substrate, followed by photoresist application to complete the process. Nanoparticle chain fabrication involves using polymethyl methacrylate on indium tin oxide-coated glass. The process includes spin coating, e-beam exposure, and development with acetone. After exposure, a lift-off technique is applied, followed by metal evaporation to form the nanoparticle chains. This precise method ensures accurate patterning essential for advanced applications. MIM fabrication involves gold deposition on a fused silica substrate using magnetron sputtering at 150 nanometers. This is followed by silicon dioxide PECVD layers of 3.3 nanometers, 56 nanometers, and 14 nanometers with no annealing and cleaving. The structure is then covered by silicon dioxide or air as detailed by Miyazaki et al. In Physical Review Letters 2006. Bragg gratings are fabricated by spin coating photoresist, followed by pre-bake and post-bake processes. Patterning is achieved through lithography, and etching is performed using potassium hydroxide and other etchants. Finally, gold is deposited via electron beam evaporation, ensuring precise layer formation for optimal optical properties. Utilize e-beam lithography with liftoff to fabricate 50 nanometer gold nanoparticles on indium tin oxide-coated glass. These particles are nearly spherical, allowing precise control over size and interparticle spacing, essential for effective plasmon waveguide fabrication. Characterization of metallic nanoparticle waveguides involves near-field scanning, optical microscopy, excitation, and far-field detection. Fabrication includes creating silica spheres using the Stoeber method with a standard deviation under 5%, surface modification with 3-aminopropyl trimethoxysilane, and attaching 1-2 nanometer gold nanoparticles. A thin gold shell is grown reductively. Near-field scanning optical microscopy is used for both excitation and characterization. The experimental setup includes a Thorlabs MDT693 piezo stage controller and a Hamamatsu infrared camera controller. Key components are the HP8164A lightwave measurement mainframe, HP816880A tunable laser, and HP81610A interface. The setup also features an HP81624A detector, Hamamatsu C5332 infrared camera, and essential optical elements like mirrors, polarizers, and objective lenses for precise characterization. Characterization methods include near-field probing, fluorescence imaging, and light scattering from surface roughness. Fourier domain observation of scattering in a grating array and optical spectroscopy are also employed. Techniques like near-field scanning, optical microscopy, NSOM, photon scanning, tunneling microscopy, PSTM, and leakage radiation microscopy provide detailed insights into material properties and surface interactions. Transmission loss in waveguides can be measured using the cutback method, prism sliding method, and scattering detection method. The prism sliding method involves a prism matching liquid and a photodetector to measure light loss. A fiber probe and lock-in amplifier enhance detection accuracy, while a recorder logs the data for analysis. Near-field scanning optical microscopy, NSOM, enhances resolution beyond diffraction limits. Aperture NSOM uses a small aperture to scan surfaces, while apertureless NSOM employs a sharp tip to interact with the sample. Both techniques provide high-resolution imaging, crucial for nanotechnology applications. Multi-application near-field scanning optical microscopy integrates 4 probes, enhancing versatility in microscopy. It combines near-field scanning optical microscopy with atomic force microscopy and scanning probe microscopy, offering comprehensive surface analysis. This integration allows for simultaneous topographical and optical data collection, providing a more detailed understanding of sample properties. Near Field Scanning Optical Microscopy (NSOM) offers high-resolution imaging beyond the diffraction limit. It utilizes a sharp probe to scan surfaces, providing detailed optical, topographical, and spectroscopic data. NSOM is crucial for analyzing nanoscale structures, enhancing our understanding of material properties and interactions at the molecular level. We've explored plasmon-assisted nanophotolithography, delving into the fabrication, excitation, and characterization of plasmonic waveguides. Special methods for characterizing metal insulator, metal insulator, metal insulator, metal insulator, and grating setups were also understood, highlighting their significance in advancing nanophotolithography techniques. Thank you for your attention. We hope this presentation has deepened your understanding of plasmonic waveguides and their applications in nanophotolithography. Your engagement is appreciated.